question 2. Okay, this is an electrochem question. A student carried out an experiment to determine the charge of the aqueous ion. So need to find what is the N here of this metal M. The student prepared 100 cm cube of 1 mole per dm cube aqueous copper 2 nitrate solution to be used in the experiment. Okay, calculate the mass of the copper nitrate trihydrate required to prepare 100 cm cube of 1 mole per dm cube copper nitrate solution. Okay, so first you need to get the mole, use the volume and the concentration, mv over 1000, you get 0.10 mole. Once you get the mole, so you can get the mass. Okay, use the molar mass times the mole, right? So molar mass times the mole, you get 24.15. Okay, so this part done. So means in order to prepare 100 cm cube of 1 mole per dm cube this solution, you need to put 24.15 into 100 cm cube of water. Okay, now for part B, describe the steps the students should take to prepare 100 cm cube of 1 mole per dm cube copper nitrate solution, starting from the mass calculated in A. So remember this one, 24.15. So we put in the steps here. Okay, how to prepare solution, and you need to give the name and capacity of any apparatus. Okay, remember the volumes that need to prepare is 100 cm cube, means we need to use the 100 cm cube volumetric flask. Okay, so let's start from the small amount of water. So put the 30 cm cube of distilled water to the small pickle and dissolve the 24.15 gram of the copper nitrate trihydrate salt. Once it's dissolved, pour the solutions to 100 cm cube volumetric flask. Okay, rinse the pickle with the distilled water and add the washing to the volumetric flask. Make sure everything's getting into the this flask. And after that, add distilled water to top up to the 100 cm cube volumetric flask to the calibration mark. Just top up, add distilled water, top up to the mark, to the calibration mark. And okay, put the stopper inward and shake the flask to homogenize the solution. Okay, that's a full plan for the solution preparation from the solid. Okay, for the part C, the students set up the electrochemical cell shown in the figure 2.1. Investigate the changing of concentration of these Mn positive, and to measure the cell potential, the E cell. Right. Okay. So the other half cell is a copper half cell, a standard copper half cell, which connects to this M cell, means the half cell with this metal M. Now suggest the function of the item labeled A. The one that labeled A is a salt bridge. Actually, when you give salt bridge, means you get the marks. It's okay. So just tell the function. The function of salt bridge is to allow ions to move between two half cells. This one is one half cell. This is one half cell. So the ions can move freely, from one side to another side. Right. Inside the salt bridge, normally we have the what do you call these the ions, the cations and anion. Right, so which can freely move to the half cells. So of course the main function is to maintain the electrical neutrality, means to prevent charge build-up. That's the main function. Okay, part D. The student used apparatus in the figure 2.1 just now to measure the cell potential. Use 6 solutions each with a different concentration. So now we have 6 different concentration, from higher concentration to smaller concentration. Now this is the cell potential, the E cell that obtained when concentration of this M cation so is decreases, the E cell increases. So this is a relation. We can use this one to further explain. Okay, so another part you need to do is this electric potential. So how to get this? So you need to refer to this equation. Okay, actually it's better for us to start from this one. E cell equal to E cathode minus E anode, right? So then if we see this part, E copper minus E cell is actually okay, this is actually the copper. This is a copper half cell. So the anode bring to left hand side, the E cell bring to right hand side. Again, the anode bring to left hand side, the E cell bring to right hand side. So we will get this. So means the half cell, the M half cell is actually anode, and the copper half cell is cathode. So to calculate this electric potential of the M, okay, Mn positive over M, so we just use the copper electric potential is given 0.337 volt minus the E cell. E cell is here. So basically you just use 0.337 minus this value, you get this value, right? Do the same calculation for all. Use the same the half cell potential for the copper, 0.337 minus 3.304, you get this one. Okay, do for all, you get all this value. Okay, make sure they are all in 3 decimal places because it's asked you to give so. Okay, so now we have all this information. The things that we are quite sure is the M electrode here, the metal M electrode is an anode. Anode means it's release electron and it's get oxidized. Okay, part E. Identify the independent variable in this experiment. Very easy because the concentration, it can be always changed, right? When concentration change, then the cell potential will change, as well as the electric potential of the M. So confirm this is concentration. We always can change this one. Then the potentials will follow. Part F1. Plot a graph on this figure 2.2 to show the relationship between the electric potential of this M and the log concentration of Mn positive. So means now, okay, this one is y-axis, this one is x-axis. Now from the table here, so you just try to plot it. Okay, so this one is again, okay, y-axis is the electric potential and the x-axis is the concentration of the M. Okay, so basically you just need to use the last 2 columns in the table, right? So the log Mn positive, so the concentration of this cation, and the electric potential of this half cell, right? Okay, one thing you need to understand and know, the concentration of the metal cation, when this M is getting lesser, as in when the concentration decreases, okay, going down, the electric potential is actually more negative. Means when the concentration is higher, then the electric potential is more positive. Remember this, when the concentration of the M is higher, then the electric potential is more positive. Okay, so use the value in the table. You just plot it. Okay, then you should get this best fit with one abnormality point around negative 3.3 here, right? The log concentration of the M. So around negative 3.3 here, you get one abnormality point. Okay, later we need to explain this. Okay, so part 2. circle the one point on the graph that you consider the most anomalous. Okay, this one. Suggest one reason why this anomaly may have occurred during the experiment procedure. Assume no error was made in the measurement of the cell potential. Okay, so first, at this the concentration, right? So the potential supposedly is somewhere around here, okay. So means the potential it should be higher. Okay, why the potential is lower than expected? Potential is only here, supposed to be here for at this concentration. Means something wrong with the concentration. Just now I told you the concentration of this cation, if it's higher, then it's more positive. So now it's less positive. Okay, because the concentration of this ion is lesser than expected. Potential is lower than expected because the concentration is getting lower. So that's the contributor for this anomalous point. So again, the concentration that used here is lower than expected, which give the less positive value, right? Okay, so that's a reason. Okay, why the answer mark scheme is this, right? The actual concentration of the solution is lower than the recorded value. The recorded value is 5 times 10 power negative 4 in the table. The actual concentration is lower because lower concentration it give less positive value. Okay, less positive value here, right? It's supposed to be more positive. Okay, for part 3, suggest how the reliability of the data shown in the table 2.1 could be improved. Okay, this one because already we got the anomalous point. In order to improve the reliability, so we just need to repeat this one. Means we need to make sure this anomalous point, we repeat it and get the result. Okay, so then it can improve the reliability. So repeat the procedure for the solutions giving anomalous point, okay, which is the point just now. So with this concentration, okay, once repeat, we might get a better results. Okay, and please do not give the general answer like repeat the procedure and so on. It must repeat for the specific set, like this one. Okay, for part G1, use figure 2.2 determines the gradient of the line of best fit. State the coordinate. You can find the two coordinates from the best fit line. These are the two coordinates I used. Okay, you can get from here, right? Once you draw the best fit, you can get from your own best fit line. Okay, so my one I get about 0.0296. Okay, so you can get yours. Make sure it's close to mine. And part 2. Okay, so we have this equilibrium. Okay, the metal M at equilibrium with its cation and with the electrons. And now the Nernst equation is given. Okay, E equal to E naught plus 2.303 times RT over NF times log concentration of the Mn positive. Okay, so all the what I call the label is here, right? The electropotential, center electropotential, okay, and all this gas constant. Just remember, this one is a standard potential. This is the one that after the deviation, after the concentration no longer standard concentration, then we will get certain electropotential, right? Okay, so the equation for the straight line is y equal to mx plus c. So just try to link this one to this Nernst equation. If you compare, then you can get all the y, m, and c. Obviously, y is the potential here, right? This one, potential, electropotential, and c is obviously the E naught. okay, the standard potential. And for the M, M is the gradient. So because just now this is the x-axis, so this whole thing is a gradient. 2.303 times RT over NF. Okay, so easy, can get 3 marks. After that, part 3, use the value that you calculate in for the gradient of your line of best fit in the G1 and the Nernst equations to calculate the value of N in this solution. Okay, the experiment is carried out at 25 degrees C. Okay, use all the information. Most importantly is you use the gradients in the part 1. Okay, my one is 0.0296. Then use the gradient 2.303 times RT over NF. Okay, R is 8.31, T is in Kelvin, which is 298 Kelvin, and Faraday constant is 96500. Okay, N is the one that I need to find. So N eventually I will get from mine I get 2, right? So means this is equilibrium. Is the M at equilibrium with this the M2 positive plus 2 electrons. Okay, N is 2 now. Okay, that's all. Thank you.